Hey, good morning, everyone. My name is DevrajChauhan, and today I am presenting my final project report on ADTA 5550 course of Deep Learning with Data. The title of the project is Convolutional Neural Network for Image Classification. In this project, I explored the use of CNN to classify the image using TensorFlow, specifically focusing on C410 dataset. I have compared the performances of MNIST and Caesar 10 dataset and implemented techniques to improve the model performances. The project was divided into several parts, each focusing on specific aspect of CNN development, from dataset selection and pre-processing of the model training, evaluation, and performance improvement. By the end of this presentation, you'll have a clear understanding how CNN works, the challenges of working with different datasets, and techniques used to improve the model performance. And let's dive into the details. So as you can see, the professor has given 8 parts of this project, and these are the table of contents. As you can see, let's start with part 1 of this project, which is use of TensorFlow directly in coding. In this part, I address the requirements of use of TensorFlow directly in coding. The project explicitly required to use TensorFlow for building, training, and testing CNN. This meant I have worked with TensorFlow lower level API rather than high level frameworks like Queso. This was a great learning experience for me because it allows me to understand the inner working of CNN, such as how layers are constructed, how weights are initiated, and how back propagation is implemented. For example, I had manually defined the convolutional layer, pooling layer, and the fully connected layer, as well as implement the forward and backward passes. Additionally, the project instructions explicitly started with Kesa API should not be used. Also, I had to implement everything from scratch using TensorFlow's code functionality. This gave me a deeper apprehensions for the complexity of building neural networks and the importance of the framework of the cases that is simplify the process. And these are the answers to those questions, which are yes, I have used the TensorFlow directly, and uh, let's move on the part second. A data set of images or audio files. I have selected the data set of images. In this part 2, I have selected Stanford dog dataset for my project. This dataset is contain 20,580 images of 120 different dog breeds. Each image is labeled with the corresponding breed. The dataset is divided into training and testing dataset of 12,000 images of training and 8,580 images of testing data. The images are in GPEG format and in very different sizes, ranging from approximately 100 into 100 pixels to 500 into 500 pixels. The labels are provided in CSV files, which makes it easier to map each images to its corresponding breed of dog. One of the challenges working with this data set is vulnerability in images and variety in images and quality. Some images are high resolution, while other are smaller and pixelated. This vulnerability requires me pre-processing the images ensuring they were all same sizes before feeding them to CNN model. The dataset is free for academic and non-commercial use, making it great resource for image classification tasks. However, due to constraints, I have decided to focus on CIFAR 10 dataset for main part of the project, as it is more widely used and easier to work with in this type of analysis. I have also provided the official website of Stanford Dog dataset and the direct download link to the dataset. Let's move forward to the part three. It's going really quickly, actually. So let's dive into the part three, which is obtain the Safer 10 dataset. In the part three, I worked with Safer dataset, which widely used dataset for image classification task. The data contains 6,000 images, colored images of 32 into 32 colored images in 10 classes, with each class 6,000 images. The classes include common objects like airplanes, cars, birds, cats, and dogs. To prepare the dataset for training, I followed the series of steps. I have downloaded the dataset. I have downloaded the dataset from the uh, official directory, that was Google Drive, which was given by the professor. The dataset is available for in composed files. I have extracted the files before using them. In second step, we have created a SSH. I have created a folder on my SSH server to organize the dataset file. This step is necessary to keep the file organized and easy to accessible during training. Using file to SSH, I uploaded the extended dataset files to SSH server. This allowed me to access the dataset remotely and train the model on more powerful machine. Moving file to created folder. Once the file was uploaded, I moved them to the created folders earlier, which were gptr slash ntbk slash effort10 data. And once the file were uploaded, I moved them to folder I created. And this step ensured that all the dataset files were in one place and ready to use. In the fifth step, I have loaded the dataset finally. I have loaded the dataset into the Python environment using TensorFlow data loading utilities. This allows me to pre-process the data and pre-process it, training the CNN model. By following these steps, was able to set up the Cepher 10 dataset for training and testing in the CNN. Let's move to the part four, where we have build, train, and test the CNN dataset. In part four, I have designed the CNN model for Cepher 10. Let's walk through the process step by step. So in this project, we have designed the build. So in Cepher 10 dataset contains of 6,000 images. As I have told you, we followed the series of steps to process the data, design the network, and evaluate the model performance. In the model design, we have the network architecture, and I have also shown you the architecture diagram over here. So in the input layer, we have it can accept the size of 32 into 32 pixels with three different color channels, RGB. In the second layer, we have first convolution layer and second convolution layer. The first one has 32 filter, and the second one has the 64 filters, each with the ReLU activation and max pooling functions. Then we have flatten the fully connected layer with the with the flattened layer, which will convert the 2D output into the 1D vector, and the 2D image will be converted into 1D vector. And here in the fully connected layer, we have 1024 neurons and ReLU activation function. And then we have the dropout layer with 50% rate to prevent overfitting. And then we have the output layer with the 10 neurons with each uh, one for each class, and softmax activation function as well. So let's discuss about the methodology that I have used in this CNN model. So before training, I pre-processed the data by normalizing the pixels value from range 0 to 1 and converting the class label into one hot encoded vectors. So I have normalized it, and the pixel value of the image were normalized in the range of 0 to 1, as I told you. And the hot class values was also the with the 1 at the index corresponding to the class and 0 elsewhere. Okay. So after this pre-processing, we have trained the model. The We have used the Adam optimizer for learning rate of 0.001 and branch size of 128. The model was trained for using 5,000 steps, and with testing model 100-step evaluate its performance. And the branch size was 128 for training, as you can see here in this diagram. The For each 100 steps of training, the module was evaluated on the testing data to calculate the accuracy, and the final accuracy was determined by 5,000 steps. And I have given the overview of how was that looking. You can see that in my files as well. So the first 100 step was for 40.39. So the model achieved the final accuracy of 82%. The accuracy improved slightly over time by starting from 40.39% over the 100 step of reaching 82% over 5,000 steps. This indicates that the model was efficiently learning from the features of CIFAR 10 dataset. So the uh, model, so the analysis, the model exhibits the typical behavior of image classification task, which accurately improves as training performed. The inclusion of dropout helped prevent overfitting, and the model generated well to the testing data. However, training time was subsequently is further tuning over improved performance. I have faced few challenges as well. So the model behavior was evaluated here. The model exhibits typical behavior of image classification task. As a training process, the network was able to learn and increasingly complex patterns result in higher accuracy. The include the dropout layer is fully connected layer help the prevent overfitting, as the accuracy of the test is contained to improve the rather than compared to each training. So there are two challenges that I faced. There are many, but these are the two challenges: training time, the large data set of CIFAR 10, and the model architecture. The training time was subsequently very high. The optimizations like using the higher branch size and adjusting the learning rate could help the speed up the model. While the model showed good performance on the testing data, further tuning could improve the generation of new and unseen data as well. In conclusion, I would say the CNN uh, was working fine, but if we can in future we can do much more things, and that we will do as we move forward with this project.